Hello guys, welcome to this session on Kubernetes introduction and architecture. Okay, here we are going to cover introduction to Kubernetes, then why we are using Kubernetes, and then Kubernetes architecture in details, and how the master node and worker node communicates. Okay, so these are all the topics we are going to cover in this particular session. Okay, when you are kind of transitioning from traditional virtualized deployment to highly scalable distributed cloud architecture, so managing thousands of kind of independent container components, okay, and that manually, okay, introduces an impossible, you can say, operation burden, because it is very hard to manage like thousands of containers, okay, manually, you can say. So that's why we introduced that uh, Kubernetes. And Kubernetes was kind of originally invented by Google and now maintained by open source standard under CNCF, that is Cloud Native Computing Foundation, and also known as Kubernetes. So it is an open source container orchestration platform designed to automate the deployment, scaling, management, and network routing of containerized applications. So now what are the key concepts here? So we have the pods, okay. So it is the smallest deployable execution unit inside a cluster. A pod wraps around one or more containers, such as your application container paired with some logging sidecar daemon, okay. Also container inside a single pod share an identical network namespace, a local host, IP address, and storage volumes. Then we have the nodes. So it is the underlying physical bare metal hardware, or you can say cloud virtual machines such as AWS EC2 instances that provide the actual raw compute power, such as vCPU, RAM, and kernel storage to host your containers. Then we have the cluster. So it is kind of an aggregated collection of master control nodes and worker nodes, and that are kind of unified into a single managed infra fabric, you can say. Then we have different services. So this, as you know, containers are transient and kind of ephemeral, and Kubernetes kind of destroys and replaces them constantly during scaling or node failures, so which cause their internal IP addresses to change. So a service act as a permanent stable network abstraction layer with a static IP address, and so that it exposes a designated group of ports to the network without the traffic disruption. Now, next one is why we are using Kubernetes. So first one is the scalability. So it can scale your compute tiers horizontally up or down inside kind of seconds to match the real-time user demands. Next one is the high availability. So it enforces continuous self-healing, and if a container crashes, a pod hangs, or an entire worker node suffers some physical hardware failure, so Kubernetes instantly detects that particular change from your declared target state, and it can spin up a replacement pod on healthy nodes and reroutes networking streams without any human interventions, you can say. And the next one is the portability. So here, abstracting infra from hypervisor, okay, allows you to deploy the same configuration across on-premises, private data center, public cloud. You can say AWS, Azure, on GCP, or some hybrid cloud or multi-cloud. Okay, so it is manages them kind of seamlessly. Next is the automation and kind of resource efficiency. So it can integrate with your existing CI/CD pipelines to maintain zero downtime, and so that a rolling update and rolling rollbacks could be there. And while packing containers on your worker nodes, it can do that with the minimum minimum downtime, and without wastage of the compute resources. So next one is the Kubernetes architecture we are going to discuss in detail. So here we have the control plane and the worker node. So like control plane, okay. So like operating across like kind of master nodes, these processes like do not host your business application code. Actually, their responsibility is to evaluate cluster telemetry, make orchestration decisions, and enforce like global security and routing guidelines. This is like for like master nodes. Inside master node, we have different components. First one is the Kube API server. It is kind of the front door for the cluster. It exposes a secure, highly scalable kind of REST APIs. So every single operational command, whether triggered by some human or human admin, like he's running some command line script or some internal service account controller or there could be some worker daemon. Okay, so all of these like should route through the API server. It authenticates the request, validate the schema, and act as a singular gateway to the cluster state. Then we have the etcd. So it is kind of a highly available, distributed, consistent kind of key value data store. It acts as an absolute kind of single source of truth for the entire cluster, you can say. So every configuration details, every pod mapping, network route, deployment, manifest, so you can say saved here. And you must like there is like a rule, okay, because every etcd manages the entire state of your infra, so it must be thoroughly like backed up and encrypted at rest and kind of separated from some general computes. Then we have the cube scheduler. Okay, like when a new pod manifest is submitted to the cluster, so the scheduler scans your active inventory of the worker nodes. So it is going to filter out nodes that lack kind of sufficient VCP and memory capacity, evaluate resource affinity rules, and it is going to inspect hardware constraint and assigns the pod to the most optimal worker node for execution. So that is Kube scheduler. Then we have the Kube control manager. So it runs like multiple background controller nodes. It could be node controller or some replication controller, and its job is to compare the actual real world like live states of your cluster against a desired target state declared that is declared in your YAML file. Now, if you request a deployment to maintain a kind of three matching pods, and suppose if one pod crashes, so it's the controller manager that instantly detects it, and it is going to instruct the API server to spin up kind of new replacement. Then we have a cloud controller manager. So it is kind of a specialized layer that interacts with the cloud provider specific APIs, and it allows Kubernetes core to interact with your kind of target cloud environment, and also like translating internal cluster requirements into kind of native cloud architecture transaction. It could be like provisioning an external cloud load balancer or kind of attaching some cloud block storage disk to some particular node. And after that we have the worker nodes. So these are the servers like which receives instruction directly from the control plane and do the actual heavy lifting of executing your business kind of container runtimes. So here we have the kubelet. So it is a tiny, you can say, native worker agent that runs on every single node in the cluster, and it is going to maintain a direct continuous communication line with the master control plane API, you can say, and it matches the assigned port target, communicates with the local container runtime to ensure like the container images are downloaded and launched, and kind of continuously kind of probes container health, reporting nodes, telemetry metrics back to the API server. And next one is the Kube-proxy. So this is the software defined kind of network layer operating on every node, and it is going to use local host network firewall parameters such as IP tables or IPVS rules, and it is using these to manage some packet routing, and it ensures that like when a packet hits a specific cluster endpoint, so it is going to map to the correct target backend, okay, across the kind of internal network fabric. Then we have the container runtime. So it is kind of a low-level software engine required to unpack, pull down, run, and kind of isolate container lifecycle from kind of underlying host operating system. So while Docker handled this initially, so now modern enterprise cluster uses highly like lightweight OCI compliant runtimes like Containerd or CRIO. And now let's see like how the end-to-end communication flow occurs. So it goes from Kubernetes CLI to control plane like API server to worker node to container runtime and then to pod services and then going to the end user. So here like an operator kind of uses the command line utility like kubectl to submit the YAML manifest, you can say, over the network, and that particular request is going to hit the Kube API server in the control plane, and this API server authenticates the identity, records the target desired state safely into the etcd cluster or the etcd data store, and then the Kube scheduler select the available, you can say, healthy worker node, and then API server communicates with the target worker node via the active Kubelet agent, and Kubelet uses the instruction and commands for the node's local container runtime and to pull the corresponding image like from the private registry, and kind of it is going to stand up that particular live pod, and at the same time like Kube-proxy is going to update local routing tables to the newly created pods, and like the system stabilizes like kind of target state. Now the public user suppose hit that particular kind of maybe load balance network IP. So the service proxy kind of dynamically distribute live traffic like directly to those particular active ports. And I think that's it from this particular session. I will see you next session. Thanks.